Hi, in this video, I'm going to go over the analysis of this half-wave rectifier shown here, driving an RL source load. So we have an AC voltage source here, Vs, on the left, and we want to supply power to this DC voltage source on the right. Might be some sort of a battery, and it's in series with a resistor and inductor. So here we want to basically analyze the current through the circuit, as well as the voltage Vx across our load. So to start off with, initially, when Vs is smaller than VDC, the diode will be reverse biased and it won't be turned on. So when Vs is less than VDC, there's no current that's going to be flowing because the diode is an open circuit. But the point at which Vs rises above VDC, the diode's going to start to become forward biased and it's going to conduct current in the circuit. And we want to find out what the current looks like. So at this point, we're just going to name this point omega t equals alpha. So at alpha, this is the point at which Vs, which is equal to Vm sine omega t, omega t equals alpha. At this point, we have Vs equaling VDC. And to solve for alpha, this point, we divide both sides by Vn and take the inverse sign. So we get sine inverse VDC over Vm. This is the point at which the diode starts to conduct. Now, when the diode starts to conduct, we're just going to model it with a short circuit. Um, so then our circuit's just going to look like Vs in series with R, L, and VDC. So if we do a KVL around this loop, we're going to get this Vs, which is equal to Vm sine omega t. This voltage source equals the voltage drop across resistor, which is Ri, and I is a function of time, plus the voltage drop across the inductor. So the voltage drop across the inductor VL is equal to, we know the equation for the inductor is L di of t over dt, plus the voltage drop across the DC voltage source, which is plus VDC. So to find the current I of t, we're going to need to solve this differential equation for I of t. Now to determine I of t of this differential equation, we can solve it by using the forced response and the natural response. So I of t in the circuit is made up of the forced response and the natural response. Now the forced response is going to come from the sources. These sources are forcing a response upon the passive components R and L. And then the natural response is kind of the intrinsic behavior of just the R and L without any of the sources there. So for the force response IF, it by itself, we can use superposition to break down IF into two parts. So the first part will be from Vs. So this Vs is Vm sine omega t, and it's driving the resistor R and inductor. And in this case, VDC is going to be shorted. And this is by superposition. We're just considering one source at a time. In the second case, we're going to zero out the AC source, but keep the DC source. So in this case, we're looking for, let's call this current I forced VAC, and let's call this current I forced VDC. So the force response is made up of the superposition of these two currents. Now, to analyze, let's start with IFVAC on the left. To start off with this circuit, we're going to apply some complex algebra. So here, the equivalent impedance of R and L, we know L, the impedance of L is J omega L, and they're in series, so we're going to have the equivalent impedance being R plus J omega L. Now, this complex number, it's a complex number in the complex plane, so the magnitude or the distance from the origin is going to be the square root of R squared plus omega squared L squared. And it's going to have an angle from the origin of the inverse tangent of omega L over R. And you can just picture this as a point in the complex plane, and we have the distance and the angle. Now, to find the current IFVAC, this is just an application of phasors. So we're going to have, let's just call this magnitude of z, and let's just call this theta. So IFVAC, we just have a voltage and an impedance. So it's going to be equal to the magnitude of the voltage, which is Vn, over the magnitude of the impedance. And then we know it's going to be a sinusoid through this linear network. So we're going to have sine omega t, which is the same phase as the source, and divided by the impedance. So the phase is going to subtract from it. So minus theta. So this is our expression that we found for IFVAC. Now, for the circuit on the right, with the DC source force response upon the resistor and inductor. So in this case, because we're looking at a DC source, J omega L with omega equal to 0 is just a short. So this is just going to be a short circuit here. So it's just the VDC driving the resistor. And in this case, the current flowing through this direction, so we're considering this as ground, is going to be VDC over R. But we want IF VDC in the opposite direction. So we're just going to have IF VDC equals negative VDC over R. So we found IF VAC and IF VDC. So in total, our force response is the sum of these two terms. Now, the next step is finding the natural response. So we found the force response here. Now we want to find the natural response. The natural response is how the circuit behaves without any of these sources present. So it's really just the resistor and inductor tied to themselves. And we're looking for the natural response, I n of t. So as in all different types of circuits, we're going to use case KVL here. So we're going to have R times IN of t, voltage drop across resistor, plus the voltage drop across the inductor VL is L din of t over dt. This is going to be equal to 0. So this differential equation is I of n plus the derivative of I of n scaled by some constant equals 0. So this we know is going to have the form of an exponential. So it's going to be in the form of AE to the power of negative t over tau, where tau is the time constant of the circuit, which is for any LR circuit is L over R. So we don't know this term A, but we can eventually find that using some initial condition in the circuit. But we found the form for I of n. So we found IN, we know IF, so we know the expression for the current through the circuit. So I of t equals IF, and IF is made up of two parts as well. So we're going to have Vm z sine omega t minus theta, the force response due to the AC source, plus the force response from the DC source, which is minus VDC over R, and then plus the natural response, which is AE to the negative t over tau. So this is our expression for the current. Now we still need to find what the value of A is. And we can do that in this way. And one more thing, let's write I of t just with as a function of omega t, because we've just been drawing our graph on this omega t scale. So instead of time in absolute seconds, we're just doing time in terms of radians, where 2 pi is equal to the period. So in this case, I omega t is, so this term we keep the same. VDC over R doesn't depend on time. But just this exponential term, we're going to add a omega t. Since we multiplied on top by omega t, we also need to divide on the bottom by omega tau. So this is our expression, and we need to find the value of A. Now A, we can determine through an initial condition, and that's when we know that at this point, alpha, omega t equals alpha, we're going to get the current equals 0, because this is the point at which the current still has not changed yet. So we can write at omega t equals alpha, this expression is just equal to 0. So if we plug in omega t equals alpha, omega t equals alpha, and and we solved the equation for A. So we would just we would isolate this term and then divide by this exponential, and we'd be able to isolate A. Um, so it's a very straightforward algebra there, and I'll just write the result. So this value of A is going to be equal to negative Vm over Z sine alpha minus theta plus VDC over R E alpha over omega tau. So this is the coefficient in front of the exponential. So we've determined the result for the current through the circuit. It's given by this expression where the coefficient A has this value. So if we were to plot this response, we would see that as the diode begins to conduct, we're going to get a current through the circuit that looks something like this. So this current through the circuit rises from 0, gets to a peak around here, and then drops down. And at this point, the equation is going to want to say that the current goes negative, as in the current changes direction in the circuit. But due to the diode is going to prevent any current from going in the opposite direction. So the diode's going to stop conducting at this point, and the current will remain 0 for the rest of the period. So this point in which the current equation wants the current to go negative, the diode's going to get reverse biased here. So this point we're going to call beta. And we can solve for beta by knowing our expression for the current and setting it to equal 0. And that's another point besides alpha in which the current is 0, which we call the extinction angle beta. Okay, now that we've found the waveform for the current flowing through the circuit, let's now think about what the waveform for Vx looks like. So let's draw this out in purple, the waveform for Vx. So when the waveform Vs has a value that's less than VDC, we know during this first interval that the diode is reverse biased, meaning that it's an open circuit. When the diode is an open circuit, that means there's no current in the circuit. So there's no current flowing through R and no current flowing through L. Therefore, the voltage drop across R and L is 0. That means Vx is just equal to VDC. So during this first interval, Vx is just equal to VDC. Now, after alpha, the diode is conducting. During this point, the diode is just modeled as a short circuit. So the node Vx is shorted to Vs. So from alpha to beta, during this interval that the diode is just a short circuit, then Vx is just going to follow Vs. And then to this point at beta, we know the diode turns off. When the diode turns off here, once again, there's no current through R and L, so no voltage drop across R and L, and therefore Vx is just equal to VDC. So we've plotted the waveform of Vx. So as a recap, let's just go through the expression for the current again. So we have this expression I omega t in terms of the forced and natural responses that we've computed. And this expression is valid for omega t less than or equal to beta and greater or equal to alpha. Otherwise, outside of this period, I omega t is just equal to 0. And we've also found the current Vx across the load. So overall, this circuit supplies power from an AC voltage source on the left to the DC voltage source. And we've gone through the analysis to find the equation for the current circulating through the circuit, as well as the waveform for Vx. So I hope you found this video helpful to further your understanding of rectifiers. And if you like this content and would like to watch more in the future, please like this video and give the channel a subscribe. Thank you.